Not all 3D printed parts are created equal. Different 3D printing technologies can create parts with vastly different qualities and mechanical properties, which makes them suitable for different applications. In this video, we'll compare the quality of the most common plastic 3D printing technologies, FDM, SLA, and SLS, including resolution, accuracy, surface finish, isotropy, water tightness, and mechanical properties. Resolution is commonly misunderstood because it can refer to different things. Typically, resolution in 3D printing means the smallest features, finest degree of detail, or level of intricate surface texturing a 3D printer can reproduce and can be measured by metrics like minimum feature size. FDM 3D printers form layers by extruding molten plastic through a nozzle, which offers lower resolution than other processes, resulting in a fairly large minimum feature size and difficulty resolving surface textures. With SLA 3D printers, the light source that cures the resin can be very precisely directed. SLA is the highest resolution 3D printing technology capable of resolving extremely fine details. SLS 3D printers form parts by using a high-powered laser to sinter together particles of polymer powder. SLS can resolve fairly small features, but certain textures can be affected by the grainy surface finish of printed parts. Accuracy measures how closely a 3D printer can reproduce the dimensions of a digital model. For all 3D printing technologies, print settings and job setup are crucial to getting accurate parts, but the different technologies each have additional considerations. For FDM 3D printers, accuracy can be affected by the repeatability of the extrusion process, printing calibration, and filament quality, as well as material choice. PLA is fairly accurate, while materials like ABS or nylon are more prone to warp. SLA 3D printers' accuracy depends primarily on the optical performance of the printer, meaning the light source and light processing unit must supply the correct amount of light. Accuracy is also affected by material choice and the forces that a part experiences during printing. Similarly, SLS 3D printers' accuracy is determined by the optical performance of that laser and how well controlled the build environment is. Since accuracy is closely tied to resolution, and SLA and SLS have higher resolution than FDM, these technologies tend to have higher accuracy. Professional 3D printers and higher quality materials with validated print settings will generally outperform low-cost solutions, regardless of technology, as precision is strongly influenced by how well the printer, material, and software are calibrated to work together. One of the most well-known differences between FDM, SLA, and SLS 3D printed parts is the difference in surface finish. FDM's layer-by-layer hot glue gun method results in layer lines that can be seen upon close inspection and support marks where the supports came in contact with the parts. Fixing these blemishes requires extensive sanding or smoothing, which can add significant time and overall hands-on labor, making it difficult to achieve consistent results and/or high throughput. SLA 3D printers create parts that are nearly indistinguishable from injection molded plastics. Their superior surface finish is ideal for final design review prototypes and end-use products, even in the consumer goods category where surface finish and smoothness are of the utmost importance. Furthermore, the lack of layer lines allows SLA 3D printers to create almost completely transparent parts. Similarly to FDM, SLA parts that were printed on supports need these to be removed. But this can be fairly simple with advanced SLA 3D printers that use light touch supports, and the support marks are smaller, making them easier to sand away than those on FDM parts. SLS 3D printed parts have a slightly rough or grainy surface finish. However, because SLS parts don't print with support structures, it's easy to achieve a uniform surface finish across the entire part. For all technologies, surface finish can be improved with post-processing solutions like media blasting and polishing, and parts made in some FDM and SLS materials can be vapor smoothed with solvents for a glossy, smooth finish. Isotropy is a concept discussed often in 3D printing. Because 3D printing creates parts one layer at a time, completed prints may have variations in strength based on the orientation of the part relative to the build area, with different properties in X, Y, and Z axes. FDM 3D printed parts are known for being anisotropic due to stronger adhesion within each layer than from one layer to the next. This anisotropy limits the usefulness of FDM for certain applications or requires more adjustments to part geometry to compensate for it. In contrast, SLA resin 3D printers create isotropic parts, which means they are uniformly strong in all directions. SLS 3D printers create parts that are anisotropic, with slight differences in strength between the Z-axis and the XY axes. While both FDM and SLS are anisotropic, FDM exhibits greater differences in mechanical performance across different axes than SLS, and SLS creates stronger parts in general. Water tightness of parts refers to the ability of a part or assembly to prevent liquid from seeping in or out. In an extensive study done by the University of Rhode Island Underwater Robotics and Imaging Laboratory, FDM 3D printed robotics enclosures failed to keep internal mechanics dry underwater for even a few seconds. SLA 3D printed parts were deemed watertight up to very high pressurization levels, and SLS 3D printed parts kept inner electronics dry under moderate pressurization levels, while vapor-smooth SLS parts were able to stay watertight under increased pressure. Last but not least, mechanical properties. All three printing technologies have material options that optimize for different properties, such as rigidity, impact resistance, and heat resistance, so there is plenty of variation within each printer type. Mechanical properties can be relatively easy to compare by looking at the material's technical data sheets and comparing the metrics that matter for your application to those of materials you may be more familiar with. As a rule of thumb, SLS produces the highest performance parts with excellent mechanical characteristics, strength, and durability resembling injection molded parts. SLA resin parts tend to become more brittle over time with UV exposure, but offer a wide range of materials for advanced applications including in-use parts. FDM offers a similar material range to SLS, but produces parts with overall inferior mechanical properties. Watch our video on comparing 3D printing materials to learn more. To sum it up, SLA or SLS will win on most metrics and produce the highest quality parts. Start by defining the performance requirements needed for your specific application, as it might be that all three processes can produce parts that fit your needs. Then consider other key factors to make the right decision. To learn more, check out our other videos on print speed, cost, materials, and ease of use.